Hello, welcome back. Here we are with our second to last instructional installment for the semester. This is the lecture for, today, Tuesday, or more properly, tomorrow, Wednesday, April 22nd. What do I have to announce? Oh, I did send out an email regarding the final exam. And in that email, it indicates that our exam, which was originally slated for Wednesday, May 6th, will still occur on Wednesday, May 6th, but now it will be done through Gradescope. Okay, so the final exam will be available on Gradescope from 9 a.m. Eastern Daylight Time, local time here, on May 6th until 9 a.m. You will have to submit it by 9 a.m. Eastern Daylight Time on May 7th. That timing is not up to me, okay? So that's an edict from the university generally that if a final exam is going to be held during finals week, then it has to be held on the day that it was originally scheduled, in this case May 6th, and it has to be available for 24 hours from 9 a.m. on the day of the exam until 9 a.m. the following day. Okay, so that timing is not negotiable. So that is when the final exam will occur. I am currently working on some review notes for the course, which I hope to have posted maybe by the end of the weekend. I'm still kind of two minds about what to do next week. I am probably going to wind up just recording some review lecture type things. I won't necessarily strictly stick to the 50-minute format. I might do it in smaller bite-sized chunks. Maybe I'll do it in chapter-by-chapter chunks or something like that. But I will try to provide some guidance through review. And also remind you a bit about the structure of the exam, which, as I've said before, is going to be very similar, to the midterm, except that it will be twice as big, so twice as many short answer questions, twice as many long answer questions, roughly speaking. Okay, so where were we? We were talking about, so let's remember, monotone functions and we had left off with the following fact. So we have f as a function from an interval to I that's supposed to be increasing. So I, an interval, and finally C, a point in I naught, an endpoint, then we gave a characterization of the limits of f as x approach C from the left and from the right. So the limit as x approaches C from the left of f is equal to the supremum of the function values f of x, where x ranges over those elements of the interval that are strictly less than C. Okay? While on the other hand, the limit as x approaches C from the right of f is given by the infimum of all the function values f of x, where x belongs to the interval, and now x is greater than C. Okay, so we had this twofold characterization of the two one-sided limits as x approaches C from the left and the right. Okay, so then we could summarize as a corollary the following. So the following are equivalent. 1, f is continuous at C, and 2, then, well, what does it mean to be continuous at C? It means that the limit, right, the limit as x approaches C of f of x is equal to f of C itself. And here, the limit is going to be equal to f of C if and only if the limit from the left and the limit from the right are both equal and equal to f of C. And so we're just going to write that down, but using the characterization that comes from these two, this sup and this inf, rather. Okay, so that f is continuous at C if and only if the supremum of the function value is f of x, where x is in I and x is less than C, that's equal to f of C, and that's equal furthermore to the infimum of the function values f of x, where x is in I, and now x is greater than C. Okay, so I've just replaced limit from the left and limit from the right with what they're equal to in this particular case of an increasing function on an interval. And you might wonder, why are we just constantly discussing increasing functions and seemingly ignoring decreasing functions? Basically, whatever is true of an increasing function, right, you can figure out the equivalent statement, what is true then for a decreasing function, just by multiplying everything in sight by -1. Okay, so that's why we don't go through the details for decreasing functions. Okay, so now let's make a definition. Right, so last time, if you recall, I had in the corner just a little diagram. Here, I'll draw it again. There it is. It's just a little tiny picture of an increasing function that happens to be discontinuous at this point, right? It has a jump discontinuity. What we want to do is write down a formula, basically, for how big that jump is, and that's going to come, well, what do you expect it to be? I expect it to be the limit from the right minus the limit from the left, and indeed that's what it is. Okay, so we're going to restrict our attention, for the sake of simplicity, to the case of a closed and bounded interval, okay, although this stuff works a little more generally. So if our interval is the closed bounded interval from A to B, and C is not equal to either A or B, in other words, C is not an endpoint, then we define the jump of f at C to be dot 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 Okay, it's going to be denoted by J sub F at C, and it's just going to be the limit as x approaches C from the right of F minus the limit as x approaches C from the left of F. Okay, and then in the, whoops, there's my computer disappearing on me. In the event that C instead is equal to one of A or B, then we can make separate definitions, which makes sense. So the jump at A, well, what happens at A, right? So you're at the, I guess, the left-hand endpoint of this interval. So there is no limit from the left. All there is f of A. But there is a limit from the right. So in the case of the left-hand endpoint A, the jump is the limit as x approaches C from the right of F minus f of A. And then similarly, the jump of F at B is going to be f of B minus the limit as x approaches C from the left of F. Okay? So at either endpoint or at some point in the middle, we have the definition of what the jump discontinuity will be, if it exists at all. Okay? And then we can provide the following characterization of continuity for increasing functions, which is just a matter of summarizing notation, really. Okay? But we'll tie it up with a nice bow. Theorem. F as above, meaning defined on the closed bounded interval A to B, and increasing, is continuous at C if and only if the jump of F at C is equal to 0. Okay? Which makes sense, right? I mean, if your function is continuous, then the limit from the left and the limit from the right should be equal, therefore this is 0. Or, in the case of the endpoints, these two quantities here would be 0 if you were continuous at the endpoints. Right? So, this is just a convenient way to summarize what it means for an increasing function to be continuous at a point C. Alrighty. So then we come to the following theorem, which is the one I was aiming for from this section. We are not going to cover really the entirety of section 5.6, so there is a bit about the inverse. So if you have a strictly increasing, okay, well, we'll talk about that in a minute, but I won't be covering everything in detail. So, theorem. Let F, once again, from the closed bounded interval A, comma, B, be increasing. It follows that the set, call it capital D, of points in the interval AB where F is discontinuous, is countable. Okay? Which is kind of interesting, right? So, again, as I mentioned in the last lecture, right, it's certainly possible to easily write down functions which are continuous nowhere, right? We have this example, the function which is equal to 0 at every rational, and then is equal to 1 at every irrational. And that's continuous exactly nowhere, and therefore the size of the set of points where the function is discontinuous is all of R, and therefore is obviously uncountable, right? So it's certainly possible that a function could have an uncountable collection of points where the function is discontinuous. However, what this theorem is saying is that if you insist that the function is increasing, then in fact that phenomenon cannot occur. That increasing functions are a little bit better behaved. Increasing functions can be discontinuous in at most countably many places. And as we shall see in the proof, in fact, somehow there's also kind of a limit to how bad things can get. Not only are there only countably many points where this function can be discontinuous, but in fact, if you have a certain size of jump, there are only finitely many points where it can have a jump that big, right? So the jumps really kind of get smaller and smaller. Okay, so let's go ahead and prove this. All right. So D, we know, is equal to the set of points X such that this jump JF of X is not equal to 0. In fact, it's better than that, right? So recall that the jump at a point X is basically the limit from the right minus the limit from the left, right? So if the jump fails to be 0, right, which is exactly what it means to be discontinuous at X, then it more than just fails to be 0. In fact, it has to be strictly greater than 0. Okay? So this is a characterization of the set D of points that we are looking for. It's the collection of all points in the interval AB such that the jump at that point is strictly bigger than 0. Oh, incidentally, I mean, if you haven't seen it yet, there is a message from the university president, should be in your email now, about the fall. I know some of you are graduating, but if you're not, the plan, unless forbidden by government, is that we will all be back in session in the fall, in person. And I guess hoping for the best. The letter does make mention of the fact that you're all young and healthy, and the fatality rate for people your age is pretty much nil, so you'll be fine. And then it pays some minor lip service to members of our community over the age of 35. Ahem. especially those with comorbidity conditions like asthma, also AHEM. But I guess we're just going to hope for the best. So, if I see you in the fall, don't breathe on me, okay? Just no. All right, so we are trying to show that this set D is countable, right? So what we're going to do first is observe something about, in some sense, how big these jumps can be, okay? So let's take a finite list of points. A less equal to x1, x2, all the way up to xn less equal to b. Okay? So this is just an increasing list of points from the interval. Then, an f of A is less than or equal to f of B, f of A, plus the jump at x1 plus all the way up to the jump at xn, and this is all less than or equal to f of B. All right, so let me explain where this pair of inequalities comes from. So let me just say parenthetically here, note that this j sub f of x, this jump at any point x, is always greater than or equal to 0 for an increasing function. Okay, it's the limit from the right minus the limit from the left, and f is increasing, therefore this thing is always greater or equal to 0. So since f is increasing, okay, and then let's draw a picture here. Let's say here's B, here's A, here are the endpoints, so that will be height f of B, and this will be f at A, okay? And let's just, let's take this situation where we just have a couple of these points, say x1 and x2, right? So our function is increasing, and then as you come to x1, note that there is nothing in here in the way that I've chosen this list of points from the interval that says that this jump quantity at any one of those points, any one of these guys here, has to be strictly greater than 0. Right? So these points, x1 through xn, they might all be just points where the function f is continuous, which is fine. Okay? In which case, this jf thing is 0. Right? So let's suppose that's the case here at x1. We just keep on running right past there. And so this tells you that jf x1 equals 0. On the other hand, you might come to x2 here, and maybe you do actually get a discontinuity. So that means that jf at x2 is greater than 0. Okay? But the idea here is that if I'm going to travel somehow from level f of A up to level f of B, then along the way I'm going to encompass every possible jump that occurs, right? No matter where they occur in this interval, right? So that no matter how many of these jump sizes I add on to f of a, oops, I should say these should be strict. I apologize. Right, so all of these points should be different. Right, so as long as none of these jumps is a repeated quantity, right, then there's no way for you to get any further than f of b by starting at f of a and adding up a bunch of jumps from the function, right? All those jumps are not big enough to get you past f of b. And so that's all that's being said here with this pair of inequalities. So now, let's take this inequality, and what we're going to do is just subtract f of a from both sides here, okay? That's a more convenient way to look at it. So this means that jf at x1 plus all the way up to j sub f at x2, or sorry, xn, rather. This is going to be less than or equal to f of b minus f of a, right? So what this is saying is, no matter how many different finitely many points you choose from the interval, if you add up all the jumps at all those points, it's always going to be less than or equal to this fixed number, f of b minus f of a. Okay? Fine. So now what we're going to do is observe that that tells you a little something about how far wrong things can go when one of these jumps is not 0. Okay? So let's, for each natural number k, let's let capital D sub k be equal to the set of x. To be specific, let's say x in AB such that the jump of f at x is greater than or equal to f of b minus f of a all over k. In other words, you take the total distance from f of b to f of a, chop it up into k equally sized parts, right? That's 1/8 of that distance. Then you're going to look at the set of all the points in the domain where the jump is at least that big. Then what this inequality up here tells you is that there cannot be more than k of these points, right? If there are exactly k of them, then adding up all the jumps at all those k points will give you equality in this inequality here. This side here will have to add up to f of b minus f of a. If you had k plus 1 points in here, we'd be in trouble. The sum of this side here would be strictly bigger than f of b minus f of a, and we can't have that, okay? So, by design, the size of d sub k is less than or equal to k. The main point is that d sub k is finite for all k in n. That doesn't mean they're all the same size, right? So for different values of k, you could get different sizes of d sub k. The larger k is, the smaller the jump is. The smaller the jump is, the more points are allowed to have a jump of that size. However, no matter what the size of jump you choose is, this d sub k thing is always going to be finite at worst. Okay? If let me say it. I'm going to put it up here. So if x belongs to D, right? So remember, D is the set of points where this function f fails to be continuous. And we know exactly what that means in terms of this j sub f thing, in terms of the jump function. It means that j sub f at x is strictly bigger than 0. So if x is in D, j sub f of x is greater than 0. Okay? So, what does that mean? Well, here's f of b minus f of a divided by k. As k goes to infinity, this quantity, f of b minus f of a over k, that goes to 0. In particular, given any number bigger than 0, like this guy, j sub f of x, I can find a sufficiently big k such that this quantity here, f of b minus f of a over k, is strictly less than jf of x. And what that means is that x then belongs to the set d sub k for that particular value of k, and indeed hence for any larger value of k. Okay, the point I'm trying to make is that as soon as you have a discontinuity, as soon as you have a point in this set D, yes, I realize there's a chalk mark right in the middle of my glasses. As soon as you have a point in D, then the jump has to be strictly bigger than 0. As soon as the jump is strictly bigger than 0, that point x has to be contained in one of these d sub k's for some k. Okay? So, x belongs to d sub k for some k in n. Thus, D has to be contained in the union of all of these d sub k's. Okay, so the set we're interested in, D, is contained in the union, the infinite union of all these d sub k's. Each one of these d sub k's is finite. Finite sets are in particular countable, and countable unions of countable sets are again countable. In other words, based on theorems that we know, this side here is countable, and any subset of a countable set is again a countable set. Okay? So, the union from k equals 1 up to infinity of d sub k is countable. Hence, D is countable. All right. So that is the last thing that we will prove and that you'll be responsible for from section 5.6 on monotone functions. There is a little more there. So there is the notion of strictly increasing functions, right? So then when x1 is strictly less than x2, then f of x1 is strictly less than f of x2. And in that case, if you have a strictly increasing function, those functions are always one-to-one. and therefore invertible. Okay? And then there's a little bit about the fact that then if you've got one of these strictly increasing functions and it happens to be continuous, then its inverse is also continuous. Okay? It's a little tedious, and I think it's vastly overshadowed by the importance of at least introducing the derivative before the end of the semester. Okay, so that's it for section 5.6, and that's it for chapter 5 in its entirety. And now we will begin to look at chapter 6, and we will finish at least what we're going to cover. We're basically only going to look at chapter 6, section 1, up to and including something called Carathéodory's theorem. So let's begin. Okay. Chapter 6. The derivative. So let's just go ahead and start with the definition. So let I be an interval C be an element of I, and F just be some function on I into the real numbers. Okay? Some number L in R is the derivative of F at C if try and squeeze this all on one board, so imagine us going back to the top here. If for all epsilon greater than 0, there exists a delta greater than 0 such that this part should hopefully be somewhat familiar. If you consider the quotient f of x minus f of c all over x minus c, you look at the distance from that quotient to L, that will be less than epsilon if the distance from x to c is not 0 and less than delta. Okay? Well, that's really just writing down the definition of the limit, so we can go ahead and say that. So i.e., the limit as x approaches c of f of x minus f of c all divided by x minus c is equal to L, which by definition then is denoted by f prime at c. Okay? So that's the definition of the derivative. It should be familiar-ish at least. So when you first see the definition of the derivative in first year calculus, usually it's presented for reasons that are still unknown to me. possibly related to James Stewart, or maybe it's just a disease that goes back further. But it always seems to be presented as f of x plus h minus f of x all over h. Take the limit as h goes to 0. I don't know why. I mean, of course, it's equivalent to this definition. This one seems to make a little more explicit, the fact that you really are headed towards C. C is the point where all the action is happening. And it also makes explicit the dependence of the derivative on the notion of slope, right? Because every single one of these quotients here, no matter which value of x you pick, is quite clearly a slope, right? It's the difference in y values divided by the difference in x values, and it's the slope of the secant line, which connects x comma f of x to c comma f of c. Okay? All right, so there you have it, the derivative. Now, of course, this does not need to exist, right? It is perfectly possible to have even a continuous function which is not differentiable. I mean, the classic example is the absolute value function, right? So if you try to compute this limit here, when c is equal to 0 for the absolute value function, you will find that the limits from the left and the right, while they both exist, are not equal, and therefore the overall limit doesn't exist, and therefore the derivative doesn't exist, which, together with the interpretation of the derivative as the slope of the tangent line, makes a lot of sense. There's no unique tangent line that you can kind of balance on the point of this graph here. Okay? However, the train does go the other way. So this is a continuous function that has no derivative at a certain point. If, however, you have a derivative at a certain point, then you are guaranteed that the function is continuous at that point. So being differentiable is a stronger condition than being continuous. So let's see why that's true. So, theorem. Let's let f be a function from I to R. C belongs to I. And suppose that f prime at C exists. It follows that f is continuous at C. Okay. All right. So, proof. The proof is really just an application of limit laws. It's an application of the rule that says that if you have two functions, each of which has a limit, as x approaches a certain value, c in this case, then the limit of the product is the product of the limits. That's all this depends on. Okay, so if x is not equal to c, then let's consider the thing that we would like to be small, right? We want f of x to tend toward f of c, right? So we would like for the limit as x approaches c of this quantity here to be 0. That's the same thing as being continuous, all right? Well, I'm going to rewrite f of x minus f of c as f of x minus f of c divided by x minus c, which I can do. That's a legal move since x is not equal to c. And then, of course, I have to multiply again by x minus c to make sure that I haven't changed anything. The idea now, however, is that I've expressed f of x minus f of c as a product of two things, right? The limit of this thing as x approaches c, I know, that's definitely 0. But the limit of this thing as x approaches c, I also know, because I've assumed that f is differentiable at c, so the limit of this thing as x approaches c is just the derivative, f prime at c. Right? So then the product rule for limits says that this limit over here as x approaches c has got to be this limit times this limit, which will be f prime at c times 0, which is 0. And that's exactly what we want. Okay, so taking so let's take the limit as x approaches c of f of x minus f of c. Well, that will be equal to f prime at c times the limit as x approaches c of x minus c, which is f prime at c times 0, which is 0, right? And that's exactly what we want. We want the limit as x approaches c of f of x minus f of c to be equal to 0. Hence, f is continuous at c. Okay. And before we leave, I guess I will just mention that, of course, there are limit laws, right, applicable to the derivative. We are not going to work them all out in detail, and of course, you should absolutely already be familiar with the rules for finding the derivative of a product, of a quotient, of a function times a constant, of a function plus another function, etc. So all of those rules definitely apply with all of their caveats, especially in the case of the quotient rule. So I'll just you are responsible for knowing what those basic rules are for differentiation, but we are not going to write them all down, nor are we going to prove them. Okay, so that is everything I wanted to cover for today. Next time we will get into Carathéodory's theorem, and maybe we will just nose into starting a little bit of review. Okay? All right, take care. Wash your hands.